Hello, ladies and gentlemen. So, today we're going to be taking a look at what light is and get started on our optics unit. So, in optics, we're going to be exploring the physics of light, the physics of things like lenses, reflection, refraction. But in order to do that, we need to understand what light actually is. So, we're going to call back to a few years ago, which is quite a while for some of you, back to grade 4, when we first approached the idea of what light was and how it sort of functioned in our world. So, light itself is made up of a whole bunch of things called photons. So, a piece of light is called a photon. This photon travels extremely, extremely fast. In fact, one single photon could travel the Earth's equator about 7.5 times per second. And for the most part, these photons will travel in straight lines in a wave form. Alrighty, so in this instance, we're seeing different photons traveling at different energy levels. Okay. In 1801, it was Thomas Young, pictured here, who demonstrated that light shows wave-like properties, meaning that as it's moving, it's not traveling like a particle would and how you would expect it to travel. Instead, follows more so like a wave. And in 1864, James Clerk Maxwell predicted that the existence of electromagnetic waves occurred, and that we can see these waves in differing power levels. Light itself does not require a medium to travel. So most things require a medium. A medium is any substance that energy can be transferred through. So if you think of, for example, sound waves need to travel through something to be heard. When I'm speaking right now, what you're hearing is my voice being replicated through pressure waves in the air. There's magnets inside of speakers that are vibrating currently right now at a frequency that we can hear. That frequency is causing a wave of sound to propagate through the air particles. When they reach your ear, you're then able to interpret those air waves as sound. This is also why if you try and speak in another sort of medium, like underwater, the sound that we hear is garbled. It doesn't come out correctly. It's because our brains aren't meant to interpret sound in that way. We interpret sound through the air. Light is unique in that it doesn't require a medium. It's transferred through radiation. So it can travel through vacuum without it needing to have any sort of medium between it to still reach the other side. Extremely important for us, otherwise the sun would not be able to give us our heat or our light. The energy produced by a star would just simply stay around the star. So by having it being able to by light being able to travel through this vacuum and not require a medium, it allows for basic fundamental life to occur on planets. Light in and of itself is a combination of electricity and magnetism that travels in the form of a very fast wave. And these waves can be considered part of something called the electromagnetic spectrum. The electromagnetic spectrum is basically the range of electromagnetic waves going from low power to increasingly high power. And it includes a whole whack ton of different things. As you can see here, we're not just dealing with simple radio wave. We're not just dealing with things like visible light, which is what we typically interpret as light. But we're dealing with things like radio waves, microwaves, infrared light, ultraviolet light, X-rays, and gamma rays. Visible light is the portion of that electromagnetic spectrum that we can see. So we can see from red all the way up to violet. That's what visible light would be considered. That's what our eyes can actually make out. But there are creatures on this earth that can actually see a little bit lower into infrared or a little bit higher into ultraviolet light. Invisible light is basically every single bit of the electromagnetic spectrum that we cannot see. We still can detect them, and we still use them for a ton of stuff. For example, radio waves. Really great example. When we're dealing with the visible light spectrum, all of the visible light bandwidths will create white light. So if we combine all of the different frequencies of light here, we end up with white light. And we can take that white light and actually split it in a prism to break out all of those different wavelengths, and we see our rainbow. We go red, orange, yellow, green, blue, indigo, and violet in all of the different colors laid out before us. Now, dealing more so with the colors of the visible light, It was Isaac Newton that discovered that white visible light is composed of these continuous sequence of colors that he called the visible spectrum. And he used the prism to show that each of those light travels at a slower speed than the rest of the speed of light, which will allow them to separate as they go through the prism. Red will slow down the most because it's sort of the least energetic of the most, while purple, red will slow down the least as it's already going pretty slow. It doesn't slow down too much, while purple will slow down the most. And you can see this breakdown occur. As the white light's entering in, we're seeing the wavelengths slow and split and come apart. And then you can see the different speeds at which these frequencies are occurring, with red having long frequencies that indicate that it's moving generally slower, while something like violet is going pretty quickly in its frequency. It's moving a bit more rapidly. It's a bit more energetic. Okay. Now, electromagnetic waves in our society, we utilize these other forms of invisible light for a whole bunch of different things. For example, the low-powered radio waves are extremely critical for our first infrastructure on transmitting sound. Without radio waves, we would not be able to transmit we wouldn't have been able to transmit messages across the world. We utilize both AM frequency and FM frequency radio waves, AM frequency being the lower power, but can travel great distances to transmit that sound, and FM being higher power but shorter range. We can utilize microwaves to heat our food and cook our food for us. They cause hydrogen molecules to vibrate rapidly, creating steam in water, which will allow for foods to cook. Infrared light can be used to heat and warm things. So generally, if you ever go to a restaurant or a fast food place and you see these heating lamps, they're utilizing an infrared light to allow for that heat to continue to warm the food. Of course, our visible light, clearly very useful, but things like ultraviolet light, or UV light, we utilize to get a tan. If you've ever gone to a tanning salon or a tanning bed, you'll notice that they utilize a certain type of light called UV light to allow us to create melanin instead of standing out in the sun. Ultraviolet light is also produced by the sun, and it's also the thing that can cause sunburns. As we're getting more and more powerful, we can look at things like X-rays, which will allow us to actually visualize things under our skin and see our bones. And then all the way up to the powerful gamma rays, which will allow us to track things in our universe, like gamma ray bursts. There are tons of different ways that we can utilize the electromagnetic waves on the EM spectrum. Refer to page 466 for some more information on those. So, now that we've talked about what light is, now we're going to talk about how light is produced. And this is the section where you guys are going to be filling out your notes. So please make sure you have this in front of you. So, how is light produced? Well, we can only see an object if light is coming from it. So, if there's no light coming from it, we can't see the object in front of us. We need to be able to detect the light using our eyes. And objects themselves can be one of two things. They can be luminous, in which they produce their own light. For example, things like a light bulb or the sun. Or they can be non-luminous, meaning that they don't produce their own light, but they do reflect the light. So this would be things like a tree, or the pencil in front of you, or the board that you're watching me from. This is all non-luminous light. So looking here, we have a picture of a sun. Is this luminous or non-luminous? This is luminous. The sun produces its own light through chemical reactions and nuclear fusion. The moon, especially the full moon that we just recently had on Monday, is this luminous or non-luminous? Hopefully you said it's non-luminous, because the moon does not produce its own light. The moon acts as a mirror, reflecting the light from the sun on the opposite side of the earth and shining it back down on us. While it does appear very, very bright in the sky, it is non-luminous. Now, when we're dealing with luminous forms of light, a couple of different things arise. We have incandescence. So a luminous incandescent object is where light is produced due to high temperatures. Eventually, we call this sort of black body radiation. So incandescent light bulbs, the old school light bulbs that we see, will have a filament of tungsten within a vacuum sealed chamber of glass. And how they work is we essentially run a current through that tungsten that becomes so hot that it starts to exude black body radiation, creating a light. This light, like a burning candle, or this light will allow for us to see, and as a byproduct will produce a ton of heat. So generally incandescent things produce a whack ton of heat. Most of the energy that is used to create the light is actually used up for heat. The same goes for a burning candle. A burning candle, while it does produce light, generally produces more heat than anything. Oh, sorry. Electric discharge also produces light. So electric discharge is produced when a current passes through a gas, which causes the glass to glow. Oxygen will glow a bright white color, as seen when we have lightning strikes. However, neon signs are huge. Henrik Geiser invented the first neon sign using neon in a tube. And if you remember all the way back to chemistry, when I showed you all of the different noble gases, each of those noble gases will have a different color when you run an electrical charge through them. In fact, each sort of element produces their own color when you run an electric current through them. Phosphorescence. This is produced when phosphors, which are special type of chemicals, can absorb UV light, store it, and then release it back as visible light that is a lower energy over a limited period of time. So this is where we get glow-in-the-dark objects. These objects are things that will charge. You sort of hold them under a light, and they'll hold on to the charge of that UV radiation for a little bit, and then emit that light back out at a lower energy level, which will give it that sickly green or blue glow that some things have. So those are where the glow-in-the-dark things come into place. Fluorescence is where an object absorbs UV light and immediately releases that light. Some laundry detergents can fluoresce. Things like highlighters can fluoresce. Lights also fluoresce. So, for example, we don't really have them in our classroom, but a lot of older schools will have things like fluorescent light bulbs. These are tubes that are filled with low-pressure mercury vapor inside, so liquid vapor, not liquid, but a mercury vapor, and it's coated on the inside of the glass with what we call fluorescent material. What will happen is an electrical current will pass through the mercury vapor from one electrode on one end of the light bulb to the other. The mercury atoms inside will get excited by that electrical current passing through them and emit UV light. That UV light is absorbed by the fluorescent material coating the light bulb and immediately start to release that as visible light, which will allow us to then see. So it produces light. The nice thing about fluorescent lights is that they use less energy to produce and produce far less heat. So these fluorescent light bulbs can produce a large amount of light without producing a whack ton of heat, and they're better and more energy efficient, which is why fluorescent lights are really, really, really big. And they were the intermediary step to a more green sort of light fixture in homes. We've now sort of moved on to another form of light, which we're going to talk about in a second right now, which is from the light emitting diode, or the LED. So the LED is essentially a small light produced as a result of an electric current that flows through semiconductors. Alrighty, so these semiconductors are super materials that allow for the passage of electricity to pass through them, and when they do, they generate a light. These are way more energy efficient than even fluorescent lights over here, and produce quite a substantial amount of light. It's very bright. However, you need many of them in a row to produce enough light to actually light up a room, which is why a lot of LED lights that are in light bulbs that we plug into our ceiling, or even light fixtures, they're not just made of one LED, but they're made up of tens or even hundreds of LEDs all lined up in a row producing electric lights. Some of you may even have some LED Christmas lights on your tree or outside of your house, as a lot of people have changed over from the incandescent light bulbs to those LED lights. Chemiluminescence is another type of luminescence that comes from producing a chemical reaction that gives off absolutely no heat as everything is converted into light. For example, a glow stick. So the glow sticks inside have two different types of chemicals, and a glass tube separate them. When you crack that glass tube and mix the chemicals, you get that nice glow. Bioluminescence is the neat one too. So this is when chemiluminescence will occur in a living organism. So chemiluminescence can also occur inside of living things. Many organisms will utilize chemiluminescence to protect themselves from predators and to lure prey or attract mates. So for example, we have a firefly down here. Fireflies, if you've ever a kid that went to go catch them, they'll blink their butts on and off using chemiluminescence. And if you were unfortunate while trying to catch those fireflies and accidentally smushed one, sometimes your hand will actually have a little bit of glow to it, as the chemicals that create the glow in the abdomen of the firefly would mix on your hand and glow for a little bit longer. But we also have these things called plankton. So this actually is a type of squid that can also chemiluminesce in the water, but we have also types of plankton that can also chemiluminesce, and oftentimes when you walk through them, it agitates them enough that they create this beautiful blue glow in the water. And lastly, triboluminescence. I think it's lastly, yeah. Triboluminescence. So triboluminescence is where we have visible light that occurs by friction. So scratching, crushing, or rubbing between certain crystals. So one form of triboluminescence occurs when you rub two quartz crystals together. You'll get some form of triboluminescence occurring. But wintergreen mints, if you get a lifesaver, a wintergreen lifesaver, and you chomp on it, you actually can create a triboluminescent glow. So the next time you guys have these wintergreen lifesavers, head to a dark room, look in the mirror, take a crunch with your teeth, and you'll see glowing occurring in your mouth. You can also have triboluminescence with duct tape. If you have duct tape in the dark and you pull that duct tape, at the site where the tape is ripping from the roll, you'll also see a glow occur based on triboluminescence. Okay, so we've learned about light, we've learned about where light comes from and how it's produced. Now we have some homework. So I would like you to read pages 463 to 469 to find all the bold-faced terms, and on page 469 answer these questions here, 1 through 7, 9, and 11. Alrighty, I will see you guys Friday. Have a good day.